Hello everyone, welcome back to Z Physics. Today we're going to be solving the 2019 OCR Exploring Physics paper. Just a little note that this is part 2 in which I'm going to be solving just the written questions, and if you're after the multiple choice questions, please check out the link in the description for a separate video. Just a little note that these are just my solutions, they're not official solutions, and check out the link in the description for the official OCR website, paper and mark scheme. Okay, so let's get started with question 16. So this question is all about waves, and we have this graph of displacement against something. Now we are told that we can use the axes in order to find the period of the wave. So if we wanted to find the period of the wave, this means that on the x-axis, the label will have to be time. And in fact, the time period is just here. Okay, so part B, a progressive wave has a wavelength lambda, frequency f, and period t. Show that the speed of the wave is given by the equation v is equal to f times lambda. Okay, well, the speed of a wave in a given medium is constant, or tends to be constant, for instance in electromagnetic waves. So we can just use the speed in general is equal to distance divided by time. Now let's set our distance equal to the wavelength. So let's just say that in one time period, one wavelength is traversed by the wave. So if your time period is t, your distance is equal to lambda, the wavelength, like so. Now the speed of a wave is in general v, so this is just v is equal to lambda over t. However, remember that your time period is 1 over the frequency, like so, and if we're dividing by fraction, it's the same as multiplying by the inverse, and the inverse of 1 over f is just equal to f. So this means that v will be equal to the wavelength times the frequency. So next one, part C. A scientist is investigating the interference of light, and we have two light rays, L and M. Light ray L is just going to go straight through between X and Y, whereas M will be slowed down by a transparent material. This question is asking us to show the difference in time for the two rays to travel between the dashed lines X and Y is 1.0 times 10 to the power of minus 15 seconds. Okay, well, L is going to go through vacuum essentially. So let's just do two columns over here. So let's have the vacuum one, which is L. The time for ray L will just be essentially our distance divided by the speed. So this will be, let's just say this will be d divided by c. Now the distance is just this distance over here, which is 1.5 times 10 to the power of minus 6. So that's going to be 1.5 times 10 to the power of minus 6 divided by the speed of light, which is 3.0 times 10 to the 8. Plugging that into a scientific calculator, we're going to get 5.0 times 10 to the power of minus 15 seconds. Now for ray M, the speed of light will no longer be 3.0 times 10 to the 8. And this is because the light ray is going to go through a material M that has a refractive index of 1.2. Remember, the refractive index is connected to the speed of light of that substance via the equation that the refractive index is a ratio of the speed of light by the speed of light in a vacuum, which is c, to the speed of light in that particular substance. So in this case, if we're looking for the speed of light in that particular substance, then this will just be equal to c divided by n, which is 3.0 times 10 to the power of 8. And we're going to divide it by the refractive index, which is 1.20, 1.20, and this will be equal to 2.5 times 10 to the 8 meters per second. Now let's repeat the exact same calculation as above, whereas rather than C 3.0 times 10 to the 8, we're just going to include this number here, 2.5 times 10 to the 8. So what I would just say is that T subscript M is equal to 1.5 times 10 to the power of minus 6 divided by 2.5 times 10 to the 8, which is just equal to 6.0 times 10 to the power of minus 15 seconds. Now in this case, remember they're just asking us to show that the difference between the two paths is 1.0 times 10 to the power of minus 15. So final step over here, I'm just going to say that, let's say the delta T is equal to, let's start with the bigger one. So I'm going to say 6.0 times 10 to the power of minus 15, take away 5.0 times 10 to the power of minus 15, which is equal to 1.0 times 10 to the power of minus 15 seconds. Okay, next one, calculate the period of the wave. Let's see how we can tackle this using all the information that we have available. So we know that for EM radiation, C is equal to F times lambda. We don't really know the frequency. However, we can say that the frequency is 1 over the time period. Now, if I plug this into here, I get that the speed of light is equal to the wavelength divided by the time period, which of course would mean that our time period is equal to lambda divided by c. Now we're actually given the wavelength in this case. So the wavelength in vacuum is 6.0 times 10 to the power of minus 7. So this means that when the wavelength is 6.0 times 10 to the power of minus 7, we need to plug in the speed of light in a vacuum, which is 3.0 times 10 to the 8, which is going to give us a time period of 2.0 times 10 to the power of minus 15 seconds. For part 3, they're asking us if the light rays are in phase at the dashed line X. So right before it enters the material, right here, those two light rays, L and M, are in phase. What will their phase difference be at essentially the end of the crossing of the material? Well, we know that the time difference from this point to this point is 1.0 times 10 to the power of minus 15 seconds. Because the time period is 2.0 times 10 to the power of minus 15, this is half of the time period. Now remember, one full oscillation is 360 degrees, so this would mean that there will be half a wavelength, half a time period apart, i.e. they will have a phase difference of 180 degrees. So moving on to part D, which is a 6-marker question. Now the most important bit of 6-marker questions is to really carefully read them. So we're given that the speed V of surface water in shallow water of depth D is given by the following equation. V is equal to the square root of GD. Now just immediately looking at that equation, we can see that we're going to have to use y is equal to mx plus c most likely, and the gradient of that will actually be root g, but we'll come to that in a bit. The speed v is about 1 meters per second for a depth of about 10 centimeters. You're provided with a rectangular plastic tray, supply of water and other equipment available. Design how an experiment can be conducted in the lab to test the validity. So that's one thing that we need to do, which is to design an experiment and how the data can be analyzed to determine a value for g, the gravitational acceleration. Okay, well, in order to design an experiment, we are going to need to produce some waves in a nice consistent manner with the same amplitude. So for our description of the experiment, which is part 1, we must produce the waves, for instance, by oscillating a block in a tray of water with the same amplitude. So this is really, really important. We're going to move a block up and down by the same amount, which will produce the same wave with the same amplitude. After that, we're going to measure the travel time of the wave from the block to the end of the tray with a stop clock. We're going to measure the distance with a ruler, then we'll simply use distance divided by time to find the wave speed. After we've done that, we're going to vary the depth of the water and then measure the speed for different depths. Then we'll essentially be populating a table of V and D and square root of D, because we're going to be using that in the equation, but additionally the average of those values. We're going to be taking multiple measurements and then taking the average. After we've done this, we're going to plot a graph of V against the square root of D. Remember, our equation is V is equal to root GD, so it's actually the square root of D that we're interested in. If the graph is a straight line through the origin, the relationship is correct. Why is that? Well, we can easily compare V is equal to root GD to Y is equal to mx plus c. If root D is on the x-axis, if the speed V is on the y-axis, then the gradient is equal to root G, which means that we can easily find the gravitational acceleration by squaring our gradient. So question 17, we have a figure which shows the variation with distance of the displacement of a stationary wave, and the word stationary is placed in bold. We know that the period of the wave is t. On the figure, we must sketch a graph to show the variation of the displacement at time t is equal to half of the time period. Okay, well, at time equal to half the time period, pretty much everything will be inverted. Let me just give you a very, very simple case. Imagine if we just had a stationary wave of just one node and one antinode and a couple of nodes over here. So this over here is our node, this here is our node. Now, if we were to go one full time period, the wave will go back to its original position. However, if we were to go half a time period forward or backwards in time, the wave will be in the inverted position. So pretty much the same thing will be happening in this graph over here. So we must sketch the variation of the displacement at time t is equal to time period over 2. So let's just do that carefully, and we must also be labeling all the nodes with n. So this here is a node just here, and we're going to have an antinode there. So let's just carefully draw those. It's a little bit trickier on a digital whiteboard, by the way, guys, so just giving a little excuse for me there. And this one here will be up here like so, and just one more like so. So this over here is a node, this over here is a node as well. And remember, a node is a point of minimum or zero amplitude. So in this case, we have all the nodes labeled. So part B, we have stationary waves are formed in a tube closed on one end, and we have some formations and we are given the frequency. So use the figure to explain how the frequency of the sound depends on the wavelength. Well, let's have a look. So if the length of the tube is L, we can see that in this case the length is equal to a quarter of the wavelength at 60 Hertz. How do I know that? Because essentially from here to here it's a quarter of a wavelength. Now here we don't quite have a full wavelength. We don't have this part here of the wavelength, so we have half a wavelength and then another quarter. So here the length is 3/4 of a wavelength. Our final length here is actually going to be 5/4 because we have one full wavelength here, and then we have an additional quarter over here, so that's 5/4 of a wavelength. So we can see that there is a definite decrease in the wavelength when the frequency is increased. We expect them to be fully inversely proportional. Now, why is that? Well, we know that V is equal to F lambda. Now, because the speed of the sound V is a constant, nothing changes, the material doesn't change, it's still just the speed of sound in air, then let's just rearrange for let's say the frequency. So the frequency will be equal to the speed of sound divided by lambda. So we expect the frequency to be inversely proportional to the wavelength. And this is fully the case. For instance, when the frequency increases by a factor of 5, so let's just say that when the frequency increases by 5 from 60 Hertz to 300 Hertz, then your lambda, your wavelength, will be decreasing by a factor of 5. From 4L to 4/5L. Now, how did I get those values? Well, I've just simply rearranged here for lambda. So if I just take that expression, I see that lambda is 4 times the length of the tube, and moving on up onto here at 300 Hertz, then lambda is 4L divided by 5. Moving on to question 18. State Kirchhoff's second law and the physical quantity that is conserved according to this law. Now, the sum of the PDs is equal to the sum of the EMFs in a loop in a circuit. This is Kirchhoff's second law. The quantity that is conserved, and this is really important, is energy. So remember, Kirchhoff's first law is all about conservation of charge. Kirchhoff's second law is all about conservation of energy. Part B. The SI base units for the ohm are given, and we need to use the equation to determine the SI base units for resistivity. I actually have a whole video on finding the base units of resistance from scratch, so if you're wondering where this comes from, please check out a link in the description. Anyways, so we're already given this, and we are given that the unit for the ohm, remember resistance is measured in the ohm, so we can say that the kilograms meters squared s to the power of -3 a to the power of -2 is equal to the resistivity. Now the base unit for the length L is just meters, and the base unit for the area is just meters squared. So we can directly rearrange, those of course are going to cancel, and we can directly rearrange for the unit for the resistivity. Let's just write down some brackets. Normally that's the convention for the unit of a certain quantity. So the base unit for the resistivity is going to be kilograms. Now meters squared times meters is going to give me m to the power of 3, s to the power of -3, a to the power of -2. And let's just write this down in the answer box. So kg meters cubed, s to the power of -3, a to the power of -2. Okay, so part C, we have a figure which shows a circuit being used, and we have some points, and for the very first part, all we need to do is essentially draw the line of best fit. Just a quick check of my line of best fit. So notice that I have one point over here and I have one point over here, and the line of best fit seems to go through the vast majority of the points. So I'm reasonably happy with my line of best fit. Now the gradient of this line of best fit, the most important thing that we can do is to take a large gradient triangle. So notice how I've taken the largest possible gradient triangle. Using then that m is equal to delta y over delta x, I found that the gradient is equal to 2.7 minus 0.6 divided by 0.7. Quick check of units, no standard units on the axis, so our gradient is about 3. Okay, next one, show that the gradient of the line is rho over AE, where rho is the resistivity, A is the cross-sectional area, and E is the EMF of the cell. Okay, well, let's start with our governing equation. R is the resistance, and this is, of course, equal to the resistivity times the length divided by the cross-sectional area. In general, R is voltage divided by current. In this case, we'll be dealing with the EMF. So let's call that E, and we're going to be dividing that by the current I, which is rho L over A. Now we have a graph up here of 1 over I against the length, like so. So we can see that this is what we were given up there. So we should really rearrange for 1 over I. So what I'm going to do is I'm going to take this equation, I'm going to divide both sides by the EMF. So what I'm going to get is that 1 over the current I is equal to rho L over A E, like so. Now our next step is simply to compare to y is equal to mx plus c. So y is equal to mx plus c. I'm going to add a little plus 0 because I can. And L is on the x-axis. 1 over I is on the y-axis. The straight line will have an intercept which is pretty close to 0. It doesn't necessarily need to be right through 0 due to errors. But our gradient, importantly, will be this quantity. So the gradient m will be equal to rho divided by AE. Now for part 3, we know that the EMF of the cell is 1.5 volts and the diameter is 0.3 millimeters. We're going to be really careful when we're calculating the cross-sectional area. Use your answer to the part 1, which was the gradient, to determine the resistivity. Okay, well, we know that our gradient is equal to the resistivity divided by AE. So just rearranging this equation for the resistivity, we know that the resistivity will be M, the gradient, times the cross-sectional area, times E, the EMF. So our gradient is 3.0. This answer will vary a little bit on your line of best fit, by the way, but the one we've got up here is 3.0 multiplied by the cross-sectional area. So the cross-sectional area will be pi d over 2 squared. So pi times, now 0.38 millimeters, so that's times 10 to the power of minus 3. We're going to be dividing that by 2 because we're given the diameter, and we're going to square this. So this guy over here, that's your cross-sectional area. And after we've done this, we need to multiply by the EMF, which is 1.5. So if we were to plug this into a scientific calculator, let's see what we are going to get. Times 1.5, we're going to get approximately 5.1 times 10 to the power of minus 7. Just a little note that this answer will vary and will be somewhere around 5 times 10 to the power of minus 7, depending on the value of your line of best fit, and that is totally fine. Final part of this question, so the figure illustrates how a student had incorrectly measured all the lengths of the wire. So we can see that the measured length is here and the actual length is here. Well, if that's the case, then all of the measured lengths will be offset by the same amount. This is a classic example of a systematic error. So we can just say that this is an example of a systematic error. Now, the good thing about systematic errors is that they don't actually affect the value of your gradient. They just offset, they just shift your graph. In this case, because the length was on the x-axis, it was 1 over the current against length. So this means that all the points will be just shifted slightly by exactly the same amount. Now, this would mean that the gradient will not be affected by this. So the systematic error, let's just say that which leads to a horizontal shift. However, the gradient will be unaffected. If there's no effect on the gradient, well, there won't be any effect on our calculation for the resistivity, because there's no effect on the gradient, there's no effect on the area, there's no effect on the EMF as well. And if that's the case, our calculation of the resistivity will be just fine. So, question 19, we have a figure which shows an electric circuit. The circuit has a parallel component over here. Now, the power supply has the electromotive force EMF and no internal resistance, so we don't have to worry about that. Then we have a graph of I against V for the LED is shown here. Now, the potential difference across the LED is 2.5 volts. So we know that there's 2.5 volts across the LED. Use the figure to show that the PD across the 50 ohm resistor is 0.5. Now, this graph will immediately allow us to see what the current is for the LED at 2.5 volts. So at 2.5, which is just here, if we were to go up here, we're going to find that the current is actually 0.01. So there's 0.01 amps, which is going across this branch of the circuit. Because the LED is actually in series with the 50 ohm resistor, then we could really easily find the potential difference across it, because the current will also be 0.01 amps through that resistor as well. So let's just do that. We're going to use V is equal to IR. So it's going to be 0.01 amps times the resistance of the 50 ohm resistor, which is, surprise, surprise, 50 ohms. And this will be 0.50 volts. For part B, we need to calculate the EMF of the power supply. Now, just for the sake of simplicity and only for the purposes of this video, I'm going to do my calculation next to that circuit. Remember, in the real exam, you need to always write down your answers within the prescribed space. Okay, well, we have the following information here. So far, we've been given that the potential difference across the LED is 2.5 volts, and we've calculated that the potential difference across this resistor is 0.5. Now, because the PDs must equal the EMFs, Kirchhoff's second law, within a closed loop, just within this loop over here. This means that across the 75 ohm resistor, we are going to have 3 volts. You can kind of think of it, if there's 3 volts across this branch, there have to be 3 volts across this branch as well. Well, what current is going through there? So the current through the 75 ohm resistor will just be equal to the potential difference divided by the resistance. So that's going to be 3.0 divided by 75, and that's 0.04 amps. So if we were to use Kirchhoff's first law, the current as it goes through here, 0.04 go through there, and 0.01 goes through these two components. So this means that overall the current will have to be 0.05 through the 100 ohm resistor. So I'm just going to write a little subscript. I100 is equal to 0.05 amps. Okay, well, we know that the PD across the 75 ohm resistor is 3 volts. If we find the PD across this guy over here, by Kirchhoff's second law, we're going to find the EMF. So let's do that. The potential difference across the 100 ohm resistor is simply going to be I100 times the resistance. So that's going to be 0.05 times 100, which is of course 5 volts. Due to Kirchhoff's second law, the sum of the EMFs will have to equal the sum of the PDs across this loop over here. So if this guy here is 5 volts, then our EMF is just 3 volts plus 5 volts, which is of course equal to 8 volts. Okay, so next part, the LED emits blue light of wavelength 4.7 times 10 to the power of minus 7 meters. Estimate the number of blue light photons from the LED per second. For that, we first off need to calculate the energy of a single photon. We're going to use the formula that E is equal to hc over lambda, and that's the energy of a single photon. H is just Planck's constant, so that's 6.63 times 10 to the power of minus 34 multiplied by the speed of light, 3.0 times 10 to the 8, and we're going to be dividing that by the wavelength, which is 4.7 times 10 to the power of minus 7, and overall this is going to give us 4.23 multiplied by 10 to the power of minus 19 joules. So that's the energy of a single photon. Now let's see whether we can find out how much energy does the LED emit per second. For that, we're going to use the power formula. So we know that the power of an LED is equal to the energy of the LED. So let's just give that E subscript LED. That's the energy emitted per unit time. So the energy for the LED will be equal to the power times the time. So VI is the power times T. Now, because the time is just 1 second, we can almost ignore that part of the equation. The voltage was 2.5. The current was 0.01 amps. So if we were to multiply those out, well, we are of course going to get just 0.025 joules. So that's the total energy emitted by the LED. In order to figure out how many photons were emitted, all we need to do is just divide those two numbers. So 0.025 divided by 4.23 times 10 to the power of minus 19 is going to give us, let's put that into a calculator, minus 19 is going to be about 5.9 times 10 to the power of 16 photons per second. Part 2, the light from the LED is incident on a metal of work function 2.3 electron volts. Explain with the help of a calculation whether or not photoelectrons will be emitted from the surface of the metal. So if the energy of the photon is above the work function, photons will be emitted. Now the only problem, or the only little problem, meaning that we cannot answer this question instantly, is because we are given two different units. We know that the energy of a photon is 4.23 times 10 to the power of minus 19, and the work function is 2.3 electron volts, whereas this is given in joules. So let's convert one into the other. What I'm going to do is I'm just going to convert the photon energy to electron volts. So the energy of a photon is going to be 4.23 times 10 to the power of minus 19 joules divided by 1.6 times 10 to the power of minus 19, and this is going to give us about 2.64 electron volts. Now we can clearly see that the energy of the photon is greater than the work function. As you can see, the energy of the photon is 2.64 and the work function is 2.3. So electrons will be emitted. So electrons are emitted. Question 20. So we have figure 20 illustrating a device used to determine the relative abundance of charged rubidium ions. We have a uniform magnetic field is applied to an evacuated chamber. We're given the direction of the magnetic field is perpendicular to the plane of the paper. And we're given that some particles are entering here and they're immediately going into circular motion. We're given quite a lot of data over here, which would be very, very useful to calculate the magnetic flux density of the magnetic field. Now, because the particles are curving, we can immediately set the magnetic force equal to our centripetal force. So we can say that our magnetic force, which is QVB, is equal to mv squared divided by r, where r is the radius. So let's just rearrange for the magnetic flux density. We're going to get that B will be equal to mv divided by qr. So let's plug in some numbers. The mass is given to be 1.4 times 10 to the power of minus 25. The speed is 4.8 times 10 to the power of 4 meters per second. Then we're going to be dividing this by the charge, which is just the elementary charge, so plus 1.6 times 10 to the power of minus 19, and we're given the radius to be 0.18. Once we plug these into a scientific calculator, we are going to get about 0.23 Teslas. So question 20, this is all about beta minus decay. Anyway, so the chemical composition of ancient rocks found on Earth can be used to estimate the age of the Earth. Nuclei of rubidium-87 decay spontaneously into the nuclei of strontium-87. Notice that in this nuclear decay, the atomic number, the nucleon number 87 remains the same. However, the proton number 37 changes to 38. If the proton number has increased, this means while the nucleon number has remained the same, this means that a neutron would have turned into a proton. Remember, this over here is your total number of protons, whereas this number here is protons plus neutrons. So if a neutron turns into a proton, the charge on the left is 0 because the neutron has no charge. The charge on the right has got to be 0, so we get an electron as well. And additionally, we get an anti-neutrino. So these are the two leptons in this case. One of them is an electron, the other one is an anti-neutrino. Now, you don't have to provide this much detail and explanation. However, I just wanted to explain the thought process that goes into solving this question. Part 2, the percentage of rubidium left in a sample of an ancient rock is 95%. Estimate the age of the Earth in billions of years. Okay, remember, if we are given the half-life, then we immediately know the decay constant. And just up here in the question, we are actually given the half-life. I'm going to be working in billions of years as long as I'm consistent, because in this case, they're asking me to give the age of the Earth in billions of years, then I'm safe to do so. Okay, well, remember, the half-life is connected to the decay constant by the following equation. Your decay constant lambda is ln of 2 divided by the half-life, so it's going to be ln of 2 divided by 49. So our decay constant is going to be equal to 0.014. Let's give it a bit more significance, because we are going to be plugging that into an exponential formula in a minute. So that's the decay constant in or billions of years raised to the power of -1. Okay, well, now let's use that into the exponential decay equation. So we know that n is equal to n naught e to the minus lambda t. Now n, if n naught is 100, then n will be 95, because there's about 95% left. So this means that this ratio n over n naught will be equal to 0.95, will be equal to e to the minus lambda, which is 0.01415 times t. Let's take the ln of both sides, and what we're going to get is that ln of 0.95 is equal to the ln of e. Remember, ln and e cancel, so it's going to be minus 0.01415 t, which means that t will be equal to ln of 0.95 divided by minus 0.01415, which is equal to approximately 3.6 billion years. So the answer for this one is about 3.6 billion years. So question 21, all about nuclear physics. So figure 21 shows stable and unstable nuclei, and the grid has number of neutrons on the vertical axis and number of protons on the horizontal axis. The key on figure 21 shows whether a nucleus is stable, emits a beta plus, or emits a beta minus particle to become stable. So we can see that those ones over here emit beta minus particles, and those ones over here emit beta plus particles. For z is equal to 7, so just over here, explain or suggest in terms of n why an isotope may emit a beta minus particle. There are too many neutrons in this case. So let's just say that there are too many n particles, neutrons, because the question says in terms of n. Now, why do they emit a beta minus particle? We don't have to write this in the question because it's a 1 marker, but in a beta minus decay, a neutron will turn into a proton. So in a way, you are transferring those excess neutrons into protons. In beta plus decay, though, which is this portion over here, there are too few neutrons. There are too few n particles. And in beta plus particles, a proton is going to turn into a neutron. Part B, inside a nuclear reactor, fission reactions are controlled and chain reactions are prevented. So we have a typical chain reaction. Describe what is meant by a chain reaction. So each fission reaction produces some neutrons, which produce more fission reactions. So the whole thing could potentially spiral out of control. But it does not, because we use control rods to absorb the neutrons. Okay, part 3. So part 3, which is an application of essentially Einstein's energy equivalence principle. The energy released in each fission reaction is equivalent to a decrease in mass of 0.19 U. Well, let's calculate. This is essentially our delta M. We can calculate our delta M by just simply converting that to kilograms. The value for this is given in the question, and that's going to be 0.19 times 1.66 times 10 to the power of minus 27 kilograms. And when we multiply those together, we're going to get 3.15 multiplied by 10 to the power of minus 28 kilograms. Now we could use E is equal to mc squared, or delta E is equal to delta mc squared. Essentially multiply our result by c squared. So it's going to be 3.15 times 10 to the power of minus 28 multiplied by 3.0 times 10 to the 8. Don't forget to square this whole expression. And once we put that into a calculator, we are going to get approximately 2.84 times 10 to the power of minus 11 joules. In order to estimate the total energy, we must find the total number of particles in this sample of uranium-235. So how are we going to do that? Remember, the formula for the number of particles is mass divided by molar mass. Good way of remembering that is m over mm, so that's your number of particles, times Avogadro's constant, so times Na. Okay, well, our mass in this case is 1 kg, and our molar mass is 0.235 kilograms per mole, multiplied by Avogadro's number, which is 6.02 times 10 to the power of 23, which is going to give us 2.56 times 10 to the power of 24 particles. Now we are ready to multiply. However, there's a catch in this question. A fuel rod in a nuclear reactor contains only 3% of uranium-235. So we have this many particles, and each of them is producing this much energy. In order to estimate the total energy output, first off, it's going to be only 3% of that. So that's going to be 0.03 multiplied by the number of particles, which is 2.56 times 10 to the power of 24 multiplied by 2.84 times 10 to the power of minus 11. Once we multiply those numbers out, we are going to get up to two significant figures, about 2.2 multiplied by 10 to the power of 12 joules. So, question 22, figure 22.1 shows two horizontal metal plates in a vacuum. And then we're given the variation of charge with distance d. The relationship seems to be inversely proportional, and what this question is asking us to do is see if we can propose and carry out a test to show that Q is inversely proportional to d. Now, what is the test? The idea here is that when two quantities are inversely proportional to one another, well, if Q is inversely proportional to 1 over d, this means that a constant exists such as Q is equal to that constant divided by d. Now, if that's the case, if we were to just rearrange for Q times d, we know that Q times d will be a constant. Our test will be to pick two values of Q and d and multiply them to see if they're constant. In reality, we would probably take much more than two values. However, for the purposes of this 2-mark question, I'm going to pick 2 points. For instance, you can see the points which I have picked over here. So I picked this point over here, and I've multiplied the value of Q, which is 10. Just be really careful with the actual prefixes, so you can see that this is nanocoulombs, 10 to the power of minus 9, and this over here is given in centimeters, 10 to the power of minus 2. So in both of those cases, for this point here and for this point over here, for 20 nanocoulombs as well, when we multiply those two values, the result is 2.6 times 10 to the power of minus 10. Oh, we've got a little typo over here, so let me just correct that. 10 to the power of minus 10. i.e. our data proves that Q is inversely proportional to D because those 2 points, when multiplied, give the same answer. Okay, moving on. Use the capacitor's equation to show that Q is inversely proportional to D. Well, the parallel capacitor equation says that C is equal to E naught A over D. This is given in your formula sheet. Although we also know that Q is equal to CV. Rearranging for C, we know that C is equal to Q over V, i.e. if we were to plug this in to here, we're going to get that Q over V is equal to E naught A over D. In other words, Q is equal to E naught AV over D. So given that those two quantities remain constant, Q will be inversely proportional to 1 over D. So question 22, figure 22.1 shows 2 horizontal metal plates in a vacuum. And then we're given the variation of charge with distance D. The relationship seems to be inversely proportional, and what this question is asking us to do is see if we can propose and carry out a test to show that Q is inversely proportional to D. Now, what is the test? The idea here is that when two quantities are inversely proportional to one another, well, if Q is inversely proportional to 1 over D, this means that a constant exists such as Q is equal to that constant divided by D. Now, if that's the case, if we were to just rearrange for Q times D, we know that Q times D will be a constant. Our test will be to pick two values of Q and D and multiply them to see if they're constant. In reality, we would probably take much more than two values. However, for the purposes of this 2-mark question, I'm going to pick 2 points. For instance, you can see the points which I have picked over here. So I picked this point over here, and I've multiplied the value of Q, which is 10. Just be really careful with the actual prefixes, so you can see that this is nanocoulombs, 10 to the power of minus 9, and this over here is given in centimeters, 10 to the power of minus 2. So in both of those cases, for this point here and for this point over here, for 20 nanocoulombs as well, when we multiply those two values, the result is 2.6 times 10 to the power of minus 10. Oh, we've got a little typo over here, so let me just correct that. 10 to the power of minus 10. i.e. our data proves that Q is inversely proportional to D because those 2 points, when multiplied, give the same answer. Okay, moving on. Use the capacitor's equation to show that Q is inversely proportional to D. Well, the parallel capacitor equation says that C is equal to E naught A over D. This is given in your formula sheet. Although we also know that Q is equal to CV. Rearranging for C, we know that C is equal to Q over V, i.e. if we were to plug this in to here, we're going to get that Q over V is equal to E naught A over D. In other words, Q is equal to E naught AV over D. So given that those two quantities remain constant, Q will be inversely proportional to 1 over D, or to D. Okay, this next one is really interesting. So figure 22.3 shows a negatively charged oil drop between two oppositely charged horizontal plates in a vacuum. Now the plates are fixed and connected to a power supply. The weight of the oil drop is 1.8 times 10 to the power of minus 14. Now in the first case, the oil drop is stationary. Now this means that the electric force must match the force of gravity. So if the force of gravity is acting downwards, the electric force will have to be equal and opposite. Therefore, the magnitude of the electrical force in this case is 1.8 times 10 to the power of minus 4. The next question, though, is really interesting. So let's just take it step by step. The potential difference between the plates is now increased to 600 volts. Well, hang on a minute. It was 200 volts initially. So in order to go from 200 to 600, we multiply by 3. So if the PD increases 3 times, the electric force will also increase 3 times. So this means that the electrical force will no longer be this much, but in fact, it's going to be about 3 times that amount. And we can actually calculate that. So that's going to be just 3 times 1.8 times 10 to the power of minus 4, which is equal to 5.4 times 10 to the power of minus 4 newtons. Given that we know that now, we can apply Newton's laws to see whether we can figure out the acceleration. So the net force, the sum of all the forces, is going to equal to Fe, and because Fg is in the opposite direction, I've said that this is equal to Fe minus Fg. Fnet is equal to mass times acceleration by Newton's second law. So Ma will be 5.4 times 10 to the power of minus 4 minus the weight, which is 1.8 times 10 to the power of minus 14. Well, there's a little typo over here, so let me just check that. Everything else is correct. So it's 1.8 times 10 to the power of minus 4. Okay, now Ma will be then just 5.4 times 10 to the power of minus 4 minus 1.8 times 10 to the power of minus 4, which is going to give us Ma to be 3.6 times 10 to the power of minus 4. Now, in order to find the actual acceleration, we need to divide by the mass. And we need to be quite careful here because we are given the actual weight. Now, remember, the weight is not the mass, and just over here on the side, I've actually calculated the mass. Given that mg, which is our weight, is 1.8 times 10 to the power of minus 4, let me just change that here. Okay, moving on to part C, which is an extended writing question with 6 marks. So we have the following experiment over here. The figure shows an arrangement used by a student to investigate the forces experienced by a small length of charged gold foil placed in a uniform electric field. As always with 6 marks, it's really important to read carefully what we need to do. So they're connected to a high voltage supply. So if it's a high voltage supply, probably they're going to be asking us to talk about safety. The angle made with the vertical by the foil in the electric field is given by the following expression. Just when we read or just when we see this expression, we should instantly be thinking about y equals mx plus c. So chances are they're going to ask us to plot tan of theta over something, probably the electric field. But let's just carry on reading for the question. The angle can be determined by taking photographs with the camera of a mobile phone. Okay, that's perfect. Describe how the student can safely conduct an experiment to investigate the relationship between theta and E. So yeah, chances are we're going to be plotting a graph of tan theta against the electric field. Identify any variables that must be controlled, and additionally how the student can safely conduct an experiment. Okay, so I'm going to make a little section on essentially each of the things that we need to do. I'm first off going to start off with the description. So in order to calculate the electric field, well, we need to use the equation V over D. So we're going to calculate the electric field using E is equal to V over D. How are we going to measure each quantity? We're going to measure V with a voltmeter. Remember, it's imperative, it's really, really important that we write down even the simplest of instruments that we're going to be using to measure anything in our experiment. So measure V with a voltmeter, we're going to measure the distance D with a ruler. We're going to vary the voltage V and hence vary the electric field and measure the angle theta using a protractor. You could have also measured it using the camera of a mobile phone as well. Really, really importantly, we're going to repeat each measurement multiple times. So multiple times for E, multiple times for V, multiple times for D, and multiple times we're going to measure the angle, and we're going to take averages. So in our table, we're going to have a table for, let's say, our first measurements of V, second measurement of V, then we're going to have V average, etc. for all the variables. We're going to plot a graph of tan theta against E. If the relationship is correct, the graph will be a straight line through the origin. So this is a really important statement, so important that I'm even going to circle it. Here's my y equals mx plus c analysis. So tan theta is on the y-axis. Just a little tip. If we ever have to prove an experiment involving a trigonometric function like sine of an angle, tan of an angle, cos of an angle, whichever one it is, we never plot the angle, just the angle. We never plot just theta on the y-axis. We always plot the actual function on the y-axis. So in this case, tan of theta goes onto the y-axis, the electric field goes onto the x-axis, and Q over W is going to be our gradient, provided Q and W are constant, but we're going to mention them that they need to be controlled. So our gradient M is Q over W. Little bits about safety. So we're dealing with a high voltage power supply. So by all accounts, we should never ever touch the terminals of a high voltage power supply. In fact, we should really make sure to even put some signs out, such as danger high voltage, for to do this experiment. Now, what variables are we going to control? The charge Q should be kept constant. So one way of keeping the charge Q constant would be to keep the supply voltage constant. The W sign here also needs to be constant, and that is the weight of the foil. So this one is easy to control. We're just going to be using the same foil. One thing to add to improve our accuracy even further, I would also say that the experiment should be done very quickly in order to avoid the leaking of any charge. So as soon as we charge almost anything, it will slowly, very slowly start to lose a little bit of its charge, depending on what the humidity of the air is, for instance. So we should try to do this one relatively quickly. Just a final check that we've looked at everything that we need to look at in this one. So yeah, we've definitely described the experiment and how we can safely conduct it. So we've mentioned something about safety, we've mentioned about the relationship, and we've identified variables to be controlled. So I'm very happy with the answer of this question, and it's time to move on to the next one. Okay, question 23, all about the X-ray tube. So an X-ray tube uses a high voltage power supply with two terminals that are connected to a cathode heater filament just here. So the filament heats up and electrons are accelerated across here. They hit the anode target, and once they hit the anode target, they decelerate and X-rays are produced. So in the exam, actually, you could describe this in words or draw a basic diagram, but you need to make sure that all of those elements are included. Pay particular attention to the high voltage power supply, the cathode heater filament element, and the anode target. The X-rays are produced when the high-speed electrons hit the target and they decelerate rapidly. In other words, their kinetic energy is converted to X-ray energy. So this is really important. I'm even going to highlight that. And the kinetic energy is converted to X-ray energy. Okay, part B, we have a beam of X-rays directed at tissues in a patient. The X-ray photons interact with the atoms of the tissues. Name and describe two other attenuation mechanisms. So the ones which I've chosen are Compton scattering. In Compton scattering, the X-ray photon is scattered with a longer wavelength and an electron is removed. And I've also chosen pair production, in which the X-ray photon is absorbed and an electron-positron pair is produced. If you would like more information about these or the other one, you could have also mentioned the photoelectric effect. I have a detailed video with loads of diagrams and explanations on exactly what happens during X-ray absorption. So please see a link in the description. Okay, final question. Explain how an ultrasound transducer can emit ultrasound. Well, an AC current is applied to a crystal. It's actually called a piezo crystal, and via the piezoelectric effect, vibrations are produced. And it's the actual vibrations, for instance, if the crystal is vibrating at over 20,000 times a second, ultrasound will be produced. Explain how the reflection of ultrasound at boundary between two tissues depends on the physical properties of the tissues. This question is all about the quantity acoustic impedance Z of the tissue. The governing equation in this case is that IR over I naught, where IR is the intensity of the reflected ultrasound and I naught is the original intensity, is equal to the acoustic impedance of one, take away the acoustic impedance of the other, over the acoustic impedance of one plus the acoustic impedance of the other, and those expressions are squared. So this is the governing equation, which tells us essentially, depending on the two acoustic materials, how much of the ultrasound will be reflected. Now, notice that if Z1 is equal to Z2, this expression just turns to 0, therefore there is absolutely no reflection. Okay guys, well done. This was the end of this question paper. Thank you very much for watching. If you have found this video useful, please give it a like and subscribe. Thank you very much, and I'll see you in the next video.